Hello class, this is the last bit of section 2.3 and it's basically on what we call the squeeze theorem. This is a final cool little way we can actually solve limits or evaluate limits when, say, other methods elude us, specifically say we can't factor or we can't use conjugating factor or we're just dealing with something kind of odd. Alright, so here's what the squeeze theorem says. Basically, it tells us to assume that the functions f, g, and h satisfy the following, where f is less than or f of x is less than or equal to g of x, which is less than or equal to h of x. In other words, g of x is trapped between f and h for all values of x near a, except possibly at a, right? Because we're dealing with limits, we don't really need any values at a, right? So if the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x, and both of those guys are both equal to L, so if these outer guys, if their limit is equal to L at a, or as x goes to a, then the limit as x goes to a of g of x must also be equal to L. So, for example here, suppose this top function here, I'm going to recolor it in red because it's kind of hard to see in black and white there. But say this is h of x, and this guy down here is f of x, and this one in the middle is g of x. So what we have here is that for all x around a, as far as we can tell, g of x is trapped between h of x and f of x. Now, if the limit of f and h match each other at a, right? If the limit of f at a is L, and the limit as x goes to a of h is L, so they're matched, that means the limit of g also has to be L when x goes to a, because it's trapped in between these two guys. Therefore, right, its limit must also match since it's trapped between these two functions. That seems pretty logical, don't you think? It kind of makes sense that, yeah, of course, functions trap, g is trapped between f and h. Therefore, if f and h ever meet, they ever match, then that means g has to match there too because it's trapped between, right? So let's look at an example where we might use the squeeze theorem. So you can see the graph behind it. Let's find the limit as x goes to 0 of x squared times sine of 1 over x. So, to be honest with you, you'll see this a couple times in Cal 1, but this really becomes useful in Cal 2. You'll see this technique used a lot in Cal 2. So, whenever we see something like this, say, you know, the x squared terms, x goes to 0, this goes to 0, but this is undefined. So it's not really a 0 over 0 case exactly, but it is still an undetermined or undefined value. We can't just plug 0 in. We're actually going to use the squeeze theorem here, obviously. Right. And how we do that is, well, basically we're looking at x squared times sine of 1 over x. We're going to use what we know about sine. Okay. So sine of 1 over x. Well, sine of any value, right? I know sine is less or greater than or equal to -1 and less than or equal to 1, right? That's one thing we know about sine, is it's trapped between -1 and 1, right? we'll use this a lot. Usually the squeeze theorem deals, and the examples you'll see, they usually deal with trig functions, specifically sine, cosine, for example. Then, now, I'm looking for x squared times sine 1 over x. So I'm going to multiply this by x squared. Okay? And we're going to get negative x squared, which is less than or equal to x squared, times sine of 1 over x, less than or equal to x squared. Okay? And now we have exactly what we want. I have sine, or my x squared sine of 1 over x, trapped, right? Trapped between two functions, negative x squared and x squared. And I'm looking at the limit as x goes to 0. So if I take the limit, so now we'll take the limit as x goes to 0 of both sides. This isn't, you know, the best way to write this, but for scratch work off to the side, it's just fine. But we'll have the limit as x goes to 0, negative x squared, is less than or equal to the limit as x goes to 0 of x squared sine of 1 over x, which is less than or equal to the limit as x goes to 0 of x squared. And these limits I can calculate on the outer part, right? The limit as x goes to 0 of negative x squared is 0. Okay. This limit is what I'm looking for. The limit as x goes to 0 of x squared sine of 1 over x. And the limit as x goes to 0 of x squared is also 0 when we plug 0 in. So what I have here is that 0 is less than or equal to this limit that we're looking for, which is less than or equal to 0. The only way this can be true, both of these can be true, is if, right, this implies that the limit as x goes to 0, x squared times sine of 1 over x is 0. So that is essentially how you use the squeeze theorem. It is you basically, either you're given the functions that you know, are trapped, or you find them, and typically they'll be trig functions, so you can start with negative 1 and 1, for example. Okay. To show you kind of what's going on here graphically, I always like to look at a graph. This on the top should look familiar. That's our u, right? That's our x squared. And on the bottom here is our u that's opening downwards. That's our negative x squared. And this in the middle, this sine curve that's getting trapped in between the two, we see that this is actually the graph of x squared sine of 1 over x. You can try graphing that in a calculator and see if you get the same thing. I have to zoom in pretty close to get a good, really good look at this. But yeah, basically what we have is that this crazy looking sine type function is trapped between x squared and negative x squared. Therefore, we see that all functions, everything, both of them, all three of them, right, squeeze down into 0. Okay, and that's what the limit as x goes to 0 is asking us about. And we can see it here graphically, that the limit of all of these functions, all three, as x goes to 0 is 0. But specifically, what this tells us is that the limit as x goes to 0 of x squared sine of 1 over x is 0. Okay, so that, ladies and gentlemen, is the squeeze theorem in a nutshell. Okay, and that pretty much finishes section 2.3. be on the lookout for a video called Examples, where I will work more examples. I'm dealing with 2.3 and the remainder of chapter 2. Cheers.